So, good morning everyone. Today we will continue with the seminars, with the solving the tasks, specific task, calculating the energy of the decay, the quantities of the radionuclides, the activity of radionuclide. And just to remind you what was previously, we will start with the simple task, but it will be one important nuance that I didn't mention before. So there is the task. We should determine the maximum kinetic energy of particles emitted during the decay nitrogen-13 to carbon-13. Thus, the first question will be what is the type of the decay? And then we know the difference in masses of parental and daughter atoms. This number is given to us. And there is no emissions of gamma quanta, so we can assume that the whole energy, the total energy of the nuclear decay will go to the maximum energy, kinetic energy of the emitted particles. But as I ask you, the first question is what is the type of the decay? And since there is no change in mass, you can assume that there is beta decay. But what is the type of the beta decay? And you see that we are going from nitrogen to carbon, and the charge of the nitrogen nucleus is 7. Yeah. And we are going to the carbon with the charge 6. And that means that there should be particle. We know it's electron or positron. And as far as the charge should be constant, it should be +1 charge. Yeah? Thus, it is positron emission, and it is beta plus type of decay. And there is one difference when we calculate the energy of the emitted particles, positrons in our case, because these positrons, they will annihilate one electron. Yeah. So these two particles will annihilate, and thus when we calculate the energy of the decay, we should take this difference in masses between parental atom and daughter atom, and also subtract the two masses of electrons, because we will lose them, and then again multiply it by this number that we know already. Yeah. So we can also calculate it as this coefficient 931.5 mega electron volts multiplied by difference in masses. And then we can simply subtract the mass of two electrons, and we know from the last lecture and from the last seminar that the one mass of electron is 511 kilo electron volts, and two masses of electrons will be 1.022 mega electron volts. So with this simple equation, we can just calculate. So we know this difference in mass. We multiply it by 935.31.5. We will get 2.220, and then minus 1022. thus we will get 1.199, let's say, mega electron volts. So it is important in the case of the beta plus decay mode to subtract these two masses of electrons. It is not the case for any other type of decays, for alpha, for beta minus, or for electron captor. It is only for beta plus decay when we should subtract two masses of electrons due to their annihilation. So now we will see how to construct such decay schemes. There is a decay scheme for bromium 80, but as you can see, there is some numbers are missing, and thus we should complete the decay scheme. And to do this, we know the difference in masses. We know masses, and we can calculate the differences in masses for each type of the decay. And let's do it. So we will start with the. Let's start with the right part of this scheme. We know that there is a formation of krypton from the bromine. That means that there is a beta minus decay. The arrows are oriented to the right position, so they are moving to the right in the periodic table, and that means that it is beta minus decay. And to calculate the energy of this decay, beta minus, we should take different in masses for kryptonium and bromine. So it will be, so let's break it. We will take mass of bromine. Minus mass of krypton. And then multiply it again with our favorite number. So you can calculate it by yourself and check if I'm doing it correctly. So I got this number, 2006 mega electron volts. But we see that there is kilo electron volts in our scheme, so let's write it in kilo electron volts. Okay. And now we can write this number. It will be the maximum energy for beta minus particles. In the case, then the decay is going directly to the ground state of the krypton. Thus, it will be the energy for these particles. So we can write it here, 206 kilo electron volts. So it is for these particles. Okay. And now, as we see, there is also emission of gamma quanta due to transition of the excited state of krypton to the ground state with the energy 618 kilo electron volts. So that means that so this is equal to, let's say, maximum energy of the first type of particles. And now we can write that the maximum energy of the beta minus particle of the second type will be this whole energy minus the energy of gamma quanta. So minus. So it will give us 1, 3, 8 kilo electron volts. Okay. Quite simple. So we can write this number here. Okay, that is all with the beta minus decay, type of decay, and we also can calculate the total intensity of the beta minus particles. These numbers marked with P, it is, we can say that it is the probability that the beta minus particles with this maximum energy will be emitted during the decay of the bromine AT. Or it is the same as the intensity of the beta minus particles with this maximum energy. So it is the total sum of these intensities, of all intensities should be equal to 1, because it should be decay, so the probability of the decay is 1, so 100%, and among these types of decay, 7% will be 7% of all atoms will decay with the emission of beta minus particles with the maximum energy of 1388 kilo electron volts, and then there is 86% of the beta particles emitted with the maximum energy of 2006 kilo electron volts. And there is another intensities of another particles. Yeah. Again, we see the line that is directed to the left in this case, and it is the not a dashed line but a solid line. That means that it is beta plus decay, and we can calculate the maximum energy of the beta plus particles. As far as there is no excited state in this case, the decay is going directly to the ground state, we can calculate the maximum energy of beta plus particles as the energy of the beta plus decay. So again, it will be a difference in masses. So again, mass of bromine minus, in this case, mass of selenium. So it will be okay, but I am not right here. We should also not to forget to subtract two masses of electrons. Yeah? And also multiplied it with this number. Or if we calculate it in kilo electron volts, to this number. So I will calculate this mass, multiplied it by this number, and simply subtract 1022 kilo electron volts. So I got this number here. So it is 848 kilo electron volts for beta plus decay and the maximum energy of beta plus particles. So we can write this number here. So for beta plus particles. And now we should calculate the first probability or intensity for electron capture process, where the electron capture, it is the dashed line. Yeah? So this dashed line means that it is electron capture decay, and we can calculate the intensity of this process. So it will be 1. So the total sum of these intensities should be 1 minus intensity so for other types of decay. So it is 0.007 minus 0.86 minus 0.026. So it will give us this number. So only 4.4% of all the atoms of bromine 80 will decay by electron capture type of decay. So we can write here that probability of this process. Okay. So, but what the particles are emitted during this process? We remember that during electron capture, we can write this like this reaction. So it will be neutron. Oops, sorry, here. Plus neutrino. So in the case of electron capture, only neutrinos are emitted. They have the exact energy, the certain number, so we can call them mono-energetic neutrinos. And we can calculate the energies. So the energy of the neutrinos will be the energy of the electron capture decay that is equal just to difference in mass multiplied by this number. So we already calculated. And minus the energy of the gamma quanta that is given here. So it will be simply this. So it will be 1, 2, or 4 kilo electron volts. So I'll go here. So the energy of the mono-energetic neutrinos will be this number. So we now solve this task. Now the next task. Now we should construct the whole scheme. We don't know how it looks for the moment, but we know that it is what type of decay. Again, here we see the difference in masses. So that there is a clear indication that it is an alpha decay, and we see that there are several energies of alpha particles. That means that the decay will go not directly to the ground state, but there will be at least 2 or maybe 3 different levels, energetic levels of the daughter radionuclide. And we see that there is also emission of the gamma quanta, 1, 2, 3, 4, 5 gamma quanta. That means that there should be 5 different transitions from the excited state to the maybe another excited state or to the ground state. And there is already a calculation that the whole energy decay for alpha particles is 6.95 mega electron volts. So we will start with just radon. And I remind you that as far as it is alpha decay, the line will be directed to the left, and it will be this double line or the thick line. And there should be 3 alpha particles emitted. So they will go to some levels. And we should understand what the energy of these levels and how they correlate with each other. And you can see that the whole energy again is 6.95 mega electron volts. And we see that the energy of alpha particle is 6.82, and there is gamma quanta with the energy of 0.13 that gives us in some exactly this number, but it will be not correct because as it was in your homework, we should calculate the energy of alpha particles as this energy of the decay and the relationship between the, in this case, polonium, mass of polonium to mass of polonium plus mass of alpha particles. And if we will take these numbers we will get exact this number. That means that the maximum energy of alpha particles without emission of any gamma quanta will be 6.82 mega electron volts, and we have this number. Thus, one of the particles with the energy of 6.82 mega electron volts will go directly to the ground state of polonium. Okay, we found our first alpha particle in the scheme, in the diagram, and now we should understand how the different levels are situated in this scheme. So we can already write another numbers, so it will be 6.56 mega electron volts and 6.33 mega electron volts. We see that the difference between these two particles will give us 0.26 mega electron volts, and we don't have this transition energy of gamma quant in our scheme. But so we can write directly that it is energy level 0.26. We can also calculate the difference between this and this alpha particles. So we will get the number for this energetic level. So it will be 0.39 mega electron volts. Thus we can write it here. And we see that there is energy of gamma quanta with this value. So we can already draw this line, draw this transition, and exclude already this number. So we know it. Also, we see that there is a difference of 0.13 mega electron volts between this and these levels. So it will be a transition with the energy 0.13 mega electron volts, and there is this number again. We can exclude it already. And there is three more numbers: 0.32, 0.19, and 0.07 mega electron volts. And we don't have these levels at the moment on our diagram. But we can see that the difference, that the sum of these two numbers, 0.19 and 0.07, will give us in total 0.26. That means that there is a level somewhere in between with the transitions of 0.07, 0.19. If we would write it in this way, it will be not correct, because we also have this number, 0.32. And there is no way to get this transition if we draw this diagram as we did it already. Thus, this level should be not 0.19, but it should be 0.07, and then it will be 0.19, 0.07, and thus the difference between these two levels will be exact, the 0.32. So now you can see that there is three excited energy levels, and we have from them five gamma transitions, 5 transitions, and 5 emissions of gamma quanta with different energy. And now we built this pretty nice diagram of the decay of radon. So this is how we can build the scheme diagram if we know the energies of the alpha particles and gamma quanta. And from these exercises you will get the understanding how to read the diagrams in different textbooks and different data books. Okay, the next one. And now we will calculate the activity of our radionuclides. For this, I will remind you the expression of the main law of radioactive decay. So it is activity is equal to lambda n, where n is the number of atoms, and lambda, it is decay constant, that is equal to natural logarithm 2 divided by half-life of the radionuclide. And our task is to calculate the absolute activity of 1 kilo of just potassium chloride, not some enriched with radioactive material, just the potassium chloride that you have in the lab, for example, in common lab. And there is a natural radionuclide, potassium 40, inside the potassium. Thus, potassium chloride is naturally radioactive material. And we know the proportion of potassium 4T in the mixture of natural isotopes, and it is this very small number. And we know the half-life of the potassium 4T. And thus we know everything. We will calculate now the activity. So we will start with the calculation of the number of atoms of potassium 4T. For this, we should calculate the amount of the potassium chloride. So it is just a mass of potassium chloride divided by its molar mass. And for this, we should simply take the mass of the natural potassium. So it is not 40. The mass of potassium we will take 39 that we take from the periodic table of elements. Okay, I will not calculate right now the numbers. I will just continue with other calculation. So it is the quantity of the potassium chloride, but it is not the quantity of potassium 4T. To calculate the quantity of potassium 4T, we should take the amount of potassium inside the potassium chloride. And in our case, it's quite simply, amount of potassium will be equal to the amount of potassium chloride, because there is one atom of potassium per one molecule of potassium chloride. And thus, we will take just simply amount of potassium chloride and multiply it with the proportion of potassium 40 inside the mixture of the natural isotopes. Then we will calculate the number of atoms of potassium 40. So it will be simply the number, the amount of potassium 40 multiplied by the Avogadro number. It is a constant number equal to 602 to 10 to 23. And so we know everything. We know mass of potassium chloride, we know its molar mass, we know the proportion of potassium 40, and we know the Avogadro number. So we will put all these numbers in this equation. So it will be natural logarithm 2 divided by the half-life of potassium 40, and then multiplied by mass of potassium chloride divided by molar mass of potassium chloride, and then multiplied by the fraction of potassium 40, and then multiplied by Avogadro number. So if we will take all this number, so natural logarithm 2, it's around 0.693. Then mass of potassium chloride, we should take it not in kilos, but in grams. The fraction of potassium 40 in natural mixture of isotopes is without no units, it's just a fraction. And the Avogadro number, it's 602 10 to 23. Mole at -1 degree. Yeah. Okay. And all this divided by molar mass of potassium chloride. That's let's write it first. So it is 39 plus 35.5 grams per mole. And now we should write the half-life of the potassium 14. And we know it in years. But if we remember that the unit of activity is becquerel, and becquerel, it is 1 disintegration per second. Thus, we should calculate how many seconds are in these billions of years. So, to calculate it, we simply multiplied years by the number of days in 1 year. Then multiplied it with the number of hours in 1 day, by minutes in 1 hour, and by seconds in 1 minute. And with this, we can calculate the activity of our potassium chloride. I get this number. $16,118, let's say, becquerels. So from this simple example, you can see that even such a common salt as a potassium chloride that most of the scientists who are working with chemicals have in the lab, it is naturally radioactive, and 1 kilo gives you 16,000 disintegrations per second. So every second in your vessel with the potassium chloride, 1 kilo, there is 16,000 of radioactive decays. So this is quite illustrative and simple demonstration on how natural radionuclides that they are contained in everywhere in our life. So we will continue, and let's go further. And now the very similar task to determine now not the absolute activity but specific activity, and specific activity can be divided by mass. It is the absolute activity divided by mass, or by the volume of the solution, or by the surface of the sample, whatever. So we divide the absolute activity by another parameter of our sample. In this case, it is just the absolute activity divided by mass, so it's becquerel per gram of samarium oxide. And there is also information about the fraction of the samarium, radioactive isotope of samarium inside the mixture of natural isotopes. And also we know the half-life of this samarium-147, this radioactive nuclide of samarium, natural radionuclide. So again, with the same start, activity is equal to lambda n, we will calculate this activity. But this is the absolute activity, and the specific activity will be this absolute activity divided by mass. Now we will calculate the number of the samarium-147 atoms. So let's take this as follows. We will calculate again the amount of samarium oxide as some mass of samarium oxide divided by its molar mass. but the amount of samarium, just samarium, will be equal not simply to the amount of samarium oxide, but by the two amounts of samarium oxide, because there is two atoms of samarium per one molecule of the samarium oxide. Thus, the amount of atoms of samarium will be twice larger than the amount of the samarium oxide. That's why we multiply the amount of samarium oxide by 2 to get the amount of the samarium. And then we can calculate the amount of the radioactive samarium. It will be simply the amount of samarium multiplied by the fraction of samarium 147. And then the number of atoms will be the amount of samarium 147 multiplied by the Avogadro number. Now we can write the whole expression as follows. So the specific activity will be lambda n divided by mass. So it will be natural logarithm 2 divided by the half-life of the samarium multiplied by the this expression showed it will be mass of samarium oxide divided by molar mass of samarium oxide. Then it will be multiplication by 2 by fraction of radioactive samarium and by Avogadro number. And all this will be divided by the mass of samarium oxide as far as it is specific activity. From this we can clearly see that these two masses will be neglected, will be annihilated, and thus we will get this simplified equation of 2 logarithm 2 and then all these numbers. I will just skip the all divided by molar mass of samarium oxide and half-life. Yeah. Okay. So now we will put all these numbers we should convert also the percentage to just a fraction, so it will be 0. Simply by dividing the percentage by 100. So it will be again 602 to 10 to 23. And then molar mass of samarium oxide. I have to check the molar mass. So it will be 2 multiplied by 100. So I don't have exact number. Let's take it just this. Plus 3.16. And all this multiplied by the half-life. That is 1.3 to 10 to 11 years. And again, we have to calculate it in seconds as this. So, and I got this number, 88.2 becquerels per gram. In these tasks, it is always important to remember about the stoichiometry of the compound. Because if we didn't multiply the amount of samarium by 2, the amount of samarium oxide, we would get the specific activity twice lower than it should be. And in some cases, it is very important not to forget it, because when you calculate, for example, the activity of your medicine or the activity of your radioactive waste, you have to know the amount of the radionuclides or what you would like to use, and thus you can calculate this activity using the stoichiometry of the compounds. Or vice versa, you can calculate the amount of the radionuclide in moles or in grams if you know the activity and you know the half-life of the radionuclide, and then you can recalculate your activity that you know to the exact value of the amount of the radionuclide. Okay, we will go further, and okay, the next task. Now we have to use so-called integral form of the decay law to understand this task and to solve this task. So what is the conditions? Initially, we have a sample that contains sulfur 35, radioactive isotope of sulfur, with the activity of 50 megabecquerels. And there was an impurity of phosphorus 32 with the initial activity of 4 megabecquerel. And we have to calculate the minimum time that is required to that the activity of the impurity will not exceed of 1% of the total activity of the sample. So in this case, we have to use this form of the radioactive decay law. It is the relationship between the activity, the initial activity, and how it changed with time. Where again, lambda is the decay constant. And as we see from this equation, we have to know the half-lives of the sulfur and phosphorus. And that are these numbers. I will just write them below. It is 7 days, and for phosphorus 32, it is 14.4 days. Okay. And what is how to solve this task? What is the problem? So we know from these equations that the activity of sulfur will change with this law. I will just write S and P for sulfur, radioactive sulfur and P, not to write the whole this number, to make it a bit simpler. Okay. And we know that the activity of impurity, that means phosphorus, should be less than 1%. That means that the minimum time will be when the activity of the phosphorus will be 1% of the total activity. So we can write that the activity of phosphorus will be only 1% of the total activity, so it is sum of activity of sulfur and phosphorus. We can open the brackets and put phosphorus in one part and activity of sulfur in another part. And we can divide both of these parts by just 0.01, so it will be 99 activity of phosphorus should be equal to activity of the sulfur. And again, we can take these expressions. So it will be 99 initial activity of phosphorus multiplied by the exponent, and it should be equal to the initial activity of sulfur multiplied by this exponent. Again, all the activities will go to one part, all the multipliers with the time will go to another part, so it will be 99 ratio of initial activity of phosphorus divided by initial activity of sulfur, and it will be equal to exponent in this degree. Okay, now we can simply take the natural logarithm of these two parts. So it will be natural logarithm 99 and here we will get this. So from this we can simply take express time as a logarithm of 99. Oops. Okay. Divided by logarithm. Oh, sorry, not by logarithm. But okay, we'll write already. We express our decay constant in the half-lives of phosphorus minus sulfur. So thus we can take already the numbers for initial activity. It will be easier. So for phosphorus it should be 4, for sulfur it will be 50, and if we multiplied it, we'll get just a natural logarithm of 7.92. Here we also can take natural logarithm of 2 out of the brackets. It will be logarithm 2. And then when we express this rest of the equation, it will be in the low part just the difference in the half-lives of sulfur and phosphorus, and it will be the multiplication in the upper part. So from this simple expression we can easily calculate the required time. So it gives us 51.5 days. In this case, it is not necessary to convert days in seconds, because we are not calculating the absolute activity or specific activity. We just calculate time, and in this case we can just take the same units as it was in our formulation of the task, so days. The only moment that all times, all these units should be, all these half-lives should be in the same units. So either it is days, or years, or I don't know, minutes, or whatever. That is the only moment. Or if it was the question of how many months it should be, or how many years or minutes, then we should convert our days to the required units. So this is quite a simple task, but again it is very illustrative how the activity of different radionuclides with different half-lives is changing with time, and that even if you have initially, let's say, quite a high content of the impurity, like 4 megabecquerels of phosphorus, it gives us around 8% of the impurity inside the sulfur, but with time this impurity decays much faster than the main component, sulfur 35 in this case. And if you store your sample for enough time, then your main component will not decay in a very big degree, but your impurity will decay much faster to 1% or even less. Okay, the next task. Sometimes when we store radionuclides like radium, for example, their decay product is a gaseous product, like radon in this case, and we will get high pressure inside the vessel if it is a sealed vessel, and it is important to calculate what will be the pressure inside this vessel to, for example, estimate the safety of the storage of this sealed vessel. And in this case, we will calculate the pressure of the radon gas that is accumulated during the storage of radium-226. So, what we have to know to solve this task? First of all, as we have to calculate the pressure, we have to remember these relationships between pressure, volume, the amount of gas, the gas constant, and the temperature. And of course it is for ideal gas, but radon it's a monatomic inert gas, so we can use this equation in quite a good certainty, or with low uncertainty. And we know volume of the vessel, we know temperature, and we have to calculate the pressure. So to calculate pressure, we need to know the amount of the radon gas that is accumulated during the storage of radium. And in this case, it is the example of the secular equilibrium as far as the half-life of the radium as a parent radionuclide is much longer than the half-life of the radon 222. And in this case, as I already mentioned, we can use the relationship between for secular equilibrium. So in this case, the activity of the daughter radionuclide will be the activity, the initial activity of parental radionuclide multiplied by these brackets minus exponent of daughter radionuclide. And after, let's say, if the time of storage is more than 10 half-lives of the daughter radionuclide, then the activity of these two radionuclide will be equal to each other. So we know that the half-life of radon gas is only, let's say, 4 days. 10 half-lives will give us 40 days, and 2 months is longer than 40 days. That means that in this case, in this task, we can assume that there is already equilibrium is reached, the secular equilibrium, and the activity of the daughter radionuclide, means radon, is equal to the activity of radium. So if we know the mass of radium, we know the half-life of radium, we can easily calculate its activity. So the activity of radium will be, again, decay constant for radium multiplied by its number of atoms, and it will be lambda, and it is mass of radium divided by its atomic mass multiplied by the Avogadro number. So we know everything to calculate this activity, and we can write the same for radon gas. So it will be lambda for radon, mass of radon, atomic mass of radon, and Avogadro number. Or, as we need to calculate the amount of the radon gas, we can simply write it like this: amount of radon and Avogadro number. So activity of radon is equal to the activity of radium. So we can use it for our task, and we can write that lambda radium, mass of radium, atomic mass of radium, Avogadro number is equal to lambda radon and amount of radon and Avogadro number. We can clearly see that we can exclude the Avogadro number. And we can express the amount of radon gas from this equation. It will be amount of radium, so it is mass of radium divided by atomic mass of radium, and then it will be this ratio. And again, if we, as we remember, lambda is equal to natural logarithm 2 divided by a half-life. Thus, we can use it here again, so it will be mass of radium divided by atomic mass of radium. And here it will be also a ratio between the half-lives of radium and radon, but it will be the reversed ratio. So it will be the half-life of radon divided by the half-life of radium. And let's calculate it now. So mass of radium is 0.1 gram, just by the conditions of the task. Atomic mass is 226. Half-life of radon gas is 3.82 days. And we have to use the same unit for half-life of radium. So we know how many years it is. Thus, we should just multiply it by number of days. And so I got this number, 2.86, let's say, 10 to minus 9 mole. So, and to solve our initial task to calculate the pressure, now we have everything. But again, it is important to express all the values in the correct units. So, number of moles will be this. So this universal gas constant is equal to 8 joule per mole per Kelvin. And just a constant, so it will be also always this number. Temperature 0 Celsius degree is equal to 273 Kelvin. And we divided it by the volume. So this volume we should express in cubic meters, because joule use meters and all the unit, standard unit is meters. So 22.4 cubic centimeters, we should multiply it by 10 to minus 6. So it is how many cubic meters in 1 cubic centimeter. Okay, so now we have all the numbers, and we are able to calculate the pressure in the vessel, the pressure of radon gas in the vessel, and it is Pascal. So it's quite a low number, the low pressure value, because the atmospheric pressure it's 100,000 Pascal, so it is not very big pressure generated by radon gas. But I will give you a task for your homework, where you will have to calculate the pressure that is attributed to the accumulated helium gas. Why it is also important? Because during the radium decay to radon, there is a generation of alpha particles, and we know that the alpha particles, it's simply helium, and it is stable helium, so it doesn't decay. That means that during the storage of radium, amount of helium is always increasing, and at certain point it can reach the pressure of helium can reach big values. So you will calculate by your own what is the pressure of accumulated helium gas inside this vessel. Okay, let's go further. Okay, the next task, again about the equilibrium, and we will see if it is a secular equilibrium or not. So there is a decay chain started with lead 210. There is a 1, 2, 3 decays. Again, we can simply guess the type of the decay. If there is no change in mass, that means it's a beta decay, and we are going to the, if we will look to periodic table, you will see that we are going to the right direction through this decay. That means that it is beta minus decay in this case, and here we see the difference in mass. It was 210 and now it's 206. the difference 4. That means that there is alpha decay, so it is 1, 2 beta, 2 beta minus decays, and only 1 alpha decay. Okay, and we are starting with 1 megabecquerel of pure lead. That means that if we will write the activities, let's say here it's lead, it is bismuth, it is polonium, and let's take the sum of all these activities. And initially, the initial step, we have only 1 megabecquerel of lead, and we don't have any other nuclides. It's pure sample of lead 210. Thus, the total activity will be 1 megabecquerel. Let's take a look on the half-lives. The half-life of lead is 22 years. The half-life of bismuth only 5 days, and the half-life of polonium 138 days. That means that the half-life of the parental radionuclide is much longer than the half-life of all the daughter radionuclides. And again, this is a case of secular equilibrium, and we can use this expression for daughter radionuclide, where 2 is daughter, 1 is parental. That's lambda 2. Here it is always important to remember that in these brackets the decay constant is for the daughter radionuclide, not for parental radionuclide. And now we have a time of 5 days. And I will rewrite this expression with the degree of 2. It will be much easier to use it. So it is 2 in the degree of time divided by the half-life of the daughter radionuclide. So for lead 210, the activity will decrease with this law, but the time 5 days is very small for lead 210 to decay. So we can assume that in this case the activity of lead will be the same. So very few amount of lead will decay. So we can simply neglect this difference. For bismuth 210, we can use this equation. Thus, 5 days is equal to 1 half-life period for bismuth. And thus, if we will put this number in this equation, what we will get? It will be this expression. And thus, it will be simply a half of the initial activity of the parental radionuclide. That means it is 0.5 megabecquerel. For polonium 210, 5 days is much shorter than the period than the half-life for polonium 210. That means that there is no polonium accumulation will be after 5 days, or it will be very close to 0. Thus, the total activity of the sample will be 1.5 megabecquerel. Please note that the total activity of the sample is increasing with time due to the accumulation of the daughter radionuclide. So the next 138 days. Again, It is too short time for lead to decay, so it will be roughly 1 megabecquerel again. Bismuth 210. 10 half-lives for bismuth will be 50 days. We have 138 days. That means that in this case, the secular equilibrium is already reached, and the activity of the daughter radionuclide, bismuth 210, will be equal to the activity of the parental radionuclide. Thus, it will be also 1 megabecquerel. And for polonium 210, 138 days is equal to 1 half-life. We can use the same expression, and it will give us 0.5 megabecquerel, and thus the total activity will be 2.5 megabecquerel. Okay, and the next example is 23 years. Let's take 22.2 years. It will be easier because it will be just the half-life of lead. So it will be 0.5 megabecquerel. So for bismuth 210, again, many years later, the secular equilibrium is already reached after 50 days. So after several years, the secular equilibrium will be still there. And thus, the activity of daughter radionuclide will be the same as the activity of parental radionuclide, thus equal to 0.5 megabecquerel. And for polonium 210, again, 22 years is longer than the 10 half-lives of for polonium 210. That means that there is also an equilibrium, secular equilibrium, between the lead 210 and polonium 210. And thus, the activity of polonium will be 0.5 megabecquerel. And the total activity of the sample will be 1.5 megabecquerel. This is, again, an illustrative example of how the total activity of the sample is increasing due to the accumulation of the activity from the daughter radionuclides. And when the secular equilibrium is reached, then the activity, so it's a long time, of both parental radionuclide, it is the activity, and the daughter radionuclide is decreasing with time according to the law of radioactive decay. So after a certain point, the activity will decrease according to the law of radioactive decay. So this is all for today. I will send you homework, and please send me your feedback before the next Friday. Goodbye for today.